Hello and welcome to Euler's method. All right, so Euler's method is just another technique that we can use to approximate the particular solution to a differential equation. Whenever we're given a differential equation, right, we're given information about some function and its derivative, or a property that a function's derivative has or second derivative has, right? And so our goal when given a differential equation is usually to figure out what is the function that satisfies that differential equation. And we do that in a number of ways. The first way that we could potentially solve a differential equation is by solving it, right? Using, I'm just going to say, separation of variables. That's the first way that we could do it. All right, the second way that we could find the solution to a differential equation is by sketching its slope field, right? And then once we have the slope field, right, we can sort of estimate, the particular solution that passes through a given point. Now, if you look at the example that I've given you right here where it says consider the differential equation y prime equals x minus y, well, I welcome you to go ahead and try, but you will not be able to solve that using separation of variables. It's a non-separable differential equation. All right, the other option that you would have at this point would be to create a slope field, and you could totally do that here. Valid method. However, hopefully you remember that when a given differential equation is a function of two variables, right here it's a function of x and y, right? It's basically telling you that the derivative is the difference between the x and y coordinate at a given point, right? Those slope fields are a pain in the neck. If its derivative just depends on one variable, x or y, that's an easy slope field to make. But when it depends on two, that's kind of a pain in the neck. All right, so here I'm going to give you a third option for how to approximate the solution to a differential equation, and that is with, Euler's method. Now, please bear in mind, right, that the first option here, right, using separation of variables, that is accurate, right? That will give you the actual solution to the differential equation, and if you have the initial condition, you can find the particular solution. All right, these two here merely approximate the solution, right? It's almost impossible to make your own slope field dead accurate, right? So a slope field and Euler's method are really just approximations for the solution to a differential equation. But hey, right, the question is always, how accurate do we need it? So if it's accurate enough, it's good enough for us. All right, so let's get to it. All right, consider the differential equation again. All right, y prime equals x minus y. All right, so we're going to try to approximate the solution that passes through the point 0, 1. Now, I happen to know some stuff about this problem already, so I'm going to be making some choices that might not be so obvious to you, and that's okay. So we want the solution that will pass through the point 0, 1. So let's label that. All right, so we're at 0, and I'm going to indicate that that's 1. All right, and now before I even do anything, I want to talk general strategy with you. Okay, so here's the gist of Euler's method, because if you were to, we will eventually put Euler's method into a formula, and if you just try to remember that formula, it's just going to be one more formula that you have to know. All right, but if you can remember what it's trying to do, it's going to be a lot easier. All right, so all we do with Euler's method is we use successive tangent line approximations from point to point to point, and then figure that when we connect those tangent lines, it is going to roughly look like the curve that we want. All right, so that's all we are doing, right, is we are starting at one point, right, that we know is on the solution curve, and then using what we know about the derivative to generate a tangent line to move to the next point. And then repeating the process, repeating the process. And again, it'll start to make more sense when we actually get to it and see what it looks like. All right, so typically we will call, all right, the point that we start at x0, y0 for obvious reasons. All right, and so all that we are going to do now at this point is try to get an estimation for what the tangent line looks like, right? We already know a point that it goes through. It has to go through 0, 1. So now we just need the slope. Oh dear, how can we get the slope of the tangent line at the point 0, 1? We have a differential equation that tells us exactly what the slope is doing at that point, right? Great. So we've got a point to start at. We know how to calculate the slope, so we can know how to move away from that first point. And now we just need to decide how far do we want to move before we stop and repeat the whole process again. All right, now this is something that will either be given to you or you have to decide. All right, so keep that in mind. All right, and that is often referred to as step size, and all it means is how far do I want to move with each successive tangent line approximation. So in this case, I'm going to say that my step size, which a lot of the time will be called, h, or you could think of it as delta x, right? How much you move along the x-axis until your next approximation. Let's make it 0.1. Obviously, the smaller that you make delta x, the smaller your step size, the more accurate your set of tangent line approximations will be. All right, so we'll start at x equals 0, and you know what, let's just do like 0.1, 0.2, and 0.3, and we'll see where that gets us. Again, so this part is arbitrary. It's a choice that you have to make, or you would be given information about the step size. And that is an H, even though it kind of looks like an N. Okay, so we know where we're starting. We know that we want to end 0.1 away from there on the x-axis, right? And then we know how to move because we have information about the slope. So let's get going. So we're going to be constructing a tangent line off the point 0, 1. So it's going to look like this. Y minus y0 equals m times x minus x0. And let's fill in what we have. All right, so we know that y0 is 1. All right, our slope we will be able to calculate. In fact, let me just do that down here. All right, so our slope, I'll say y prime, right, at 0, 1. Oh, well, y prime is given by your x-coordinate minus your y-coordinate. So that's going to be 0 minus 1, which is negative 1. So let's put that in here. Then we know that x0 is 0. We also know our next x-coordinate. All right, so I'm actually going to go ahead and call these points y1 and x1. All right, meaning my next set of x and y coordinates, okay? And we know what x1 is because we decided that we were going to increment by 0.1, right? This is our h, this is our delta x, right? So we know that x1 must be 0.1. So we can put that in. Okay, and so now if you just do your arithmetic and solve, or rather just evaluate and simplify, you will be able to figure out what your next y-coordinate is, right? If you manipulate this, you'll be able to figure out that y1 is 0.9. So guess what we have now, right? We have a y1 and we have an x1. So we know where our next point is that we should plot. So our next point will be x equals 0.1 and y equals 0.9. So let's graph that. So here's 0.9, and then here's x equals 0.1, so our next point will be here-ish. Okay? And then let's connect those, right? Because after all, we were making a tangent line. Let's try that again. Okay, that's not terrible. Great. All right, so now we need to repeat this process, all right? And so we're going to be using our information about the slope and where we currently are to get to our next point. All right, so let's go again. So now what I'm really going to be setting up is, right, if we label this as x1, y1, we are now looking for x2, y2, right? We're looking to move to our next point and figure out where it is. All right, so I can set up my equation as y2 minus y1 equals m times x2 minus x1. And then we'll just fill in the information that we have. All right, we don't know what y2 is. That's kind of what we're looking for. y1 we calculated to be 0.9. Oop, we'll need our slope at that point. All right, so basically I'm going to be trying to calculate y prime at x equals 0.1 and y equals 0.9. And again, our slope is just given by x minus y, so that's going to be 0.1 minus 0.9, which is negative 0.8. Great. So that's our slope, negative 0.8. And then x2, we know what x2 is, right? We decided that we were incrementing x by 0.1. So if we're currently at x equals 0.1, our next x is going to be 0.2. And x1 was 0.1. Okay, so now if you condense this and solve for y, you'll get that y2 equals 0.82. Great, so now again, we have an x-coordinate and a y-coordinate that we can plot on our graph. All right, so I'm going to be plotting 0.82 for y and 0.2 for x. So I'm just going to label this here as 0.8. And I'll just have to plot like a little bit above it. So maybe here-ish. Okay. And then again, let's try to connect that with a tangent line. Nope. Sure. Okay. All right, and let's go do this one more time, all right, to figure out what our next point is. All right, so just one more iteration here. I'm gonna come over here. I'm running out of room. Okay, so now we will be looking for our next ordered pair. Again, I know that the x-coordinate is 0.3, but I need to know what the y-coordinate there should be. So I will set up y3 minus y2 equals m times x3 minus x2. Okay, so y3 is unknown. y2 we just calculated to be 0.82. The slope we will get from the differential equation. So y prime at the point x equals 0.2 and y equals 0.82 will be x minus y, right? And that will give us, should give us negative 0.62. So we'll put that at negative 0.62. And then x3 will be 0.3, and x2 will be 0.2. And when you simplify all of that and solve for y3, you should get that y3 equals 0.758. So let's plot that. All right, I'm going to call this right here 0.7. So I am plotting the point. 0.3 for x and 0.758 for y. So maybe about here. All right, and then let's make the tangent line. That's a tangent line. Okay, so hopefully we can maybe get a rough sense for what the curve is doing, knowing that this should be a curve. All right, and so we could then say, oh, okay, so it looks like maybe my actual curve is doing something like this, at least in this area. Okay, and again, your sketch will be much better than mine. But that's the general idea of what we are doing. We're using successive tangent line approximations, all right, to move from one point to the next. And the way that I think about it is that you always have to use the slope at the previous point to get to your next point, because you don't know what your next point is, right? So how could you know what to do to calculate your slope if you don't know what x and y are? So you need to be using the slope at the previous point to get to your next point. Okay, so let's generalize. And let's think about what we did. All right, so really what we did was we said, all right, like y3 minus y2 equals m times x3 minus x2. All right, so in other words, yn, right, whatever that happens to be, y3, y7, y2, whatever, and then you subtract, right, the y at the previous point. So yn minus 1 equals m times, and then the difference in your x coordinates, x sub n minus x n minus 1. Okay, and now there are a few things to note. This bit here, xn minus xn minus 1, well, that's just your difference in x coordinates, which is established by your choice for h, by your choice for delta x. So we can replace this with delta x or h, whatever you're comfortable with. I'm going to use h just so you get familiar with it. And then we also know that our slope will be given by the differential equation. That will just be y prime at your previous x value, right? Like I had said before, you are using the slope at the previous point to get to your next point because your next point is currently unknown. All right, so I'll say y prime of x sub n minus 1. All right, so now let's clean this up a little bit and get ourselves to something useful. All right, so we could say from here that minus yn minus 1 equals y prime of x sub n minus 1 times h. Or if you want to think about it as solving for y, right? Giving an explicit representation for your next y coordinate, right? You could write it like this, that your next y coordinate will be given by, and then you just, isolate using algebra, times h plus y sub n minus 1. All right, so whichever of these formats is helpful for you, but I would say that this is sort of the most common. But again, this just becomes a thing to memorize unless you understand what it's doing. All right, and you'll never be asked to do this, ad infinitum, right? You'll be asked to do it for a couple iterations. So if you can logic your way through it, that's fine too. All right, on to the next thing. Okay, let's take a look at some examples. And here where it says multiple representations of Euler's method, that just refers to the fact that you're going to want to be comfortable applying Euler's method to any situation, whether it is given in a formula, like this example, or a table, like the next example, or the information is somehow communicated to you in a graph. So that's what I'm talking about here. All right, so for example 1, it says given the differential equation, y prime equals x plus 2, and y of 0 equals 3, find an approximation for y of 1 using Euler's method with 2 steps. Okay, so they've already given us a bunch of information here. So let's zoom in a little bit, all right, and see if we can pick apart what they've already told us. All right, so they told us that we need to use Euler's method with 2 steps. All right, we were also given an initial condition, right? Something about y of 0, so when x is 0, and we want to approximate y of 1, so where x is 1. So we need to get from x equals 0 to x equals 1 in 2 steps. So that should infer for us our step size, right? We need to travel a distance of 1 in 2 steps, so that informs us that h is a half, right? So sometimes they'll say using, a step size of a half, or sometimes that'll sort of be embedded in the problem and you have to tease it out a little bit. All right, okay, great. So let's get started. All right, and we know that y of 0 equals 3, all right? So I'm just gonna put this on a graph again. I kind of know where the problem is going, so I'm just gonna put this here. All right, so this is our initial condition. All right, this is 3. You're a 3. All right, and this is our initial x and y. Okay, so now, let's just label our x-axis just in case. So we've got 0, then we'll have a half, and ultimately our goal is to approximate y of 1. So once we get there, we're done. Okay, so, all right, so let's begin. All right, so we know that x0, y0 is 0, 3. So first, we're going to find our next y value. We know our next x value, we just need the y that goes with it. All right, so just to reiterate, it's gonna look something like this. y1 minus y0 equals m times x1 minus x0, right? But we had sort of scooted this around. We know that x1 minus x0, oh, that's just our step size, that's just h. And if we want to explicitly solve for y1, we can by adding y0 back to both sides. And I'm going to do that just to move things along a little more quickly. So I'm going to say that this is m times h plus y0. And of course, by m, I know that that refers to our slope. All right, so let's get that. Let's get y prime of 0, 3, because that's the point that we're starting at. And so the differential equation given to us said that dy dx was x plus 2. Okay, so it only depends on x. I guess that's nice. So x plus 2 means 0 plus 2. Cool, so y prime of 0 is 2. So let's plug that in. So our next y value will be given by 2 times our step size h, which was a half, plus y naught, which was 3. And so that gets us to 4. So let's go up, let's put that on the graph. All right, so we're going to have a half and, whoops, 4. 1/2 and 4. And here's our little tangent line, all right? So that is, again, the line tangent to the point 0, 3, and we've just extended it out half a unit to get to our next point. All right, so this point right here is officially x1, y1. All right, and then we just have to do this one more time to approximate y of 1. Okay, so then in our second step, we can say that y2 will be given by, right, our slope. Now, well, I'll just write m for now, times our step size plus y1. All right, then we just need to go get y prime of 0.5 comma 4. Again, we don't really need the 4 because our derivative is only a function of x, but it's not wrong. Okay, so then our derivative is given by x plus 2, so that's 0.5 plus 2, all right, which is 2.5. Okay, so let's plug that in. So then y2 equals our slope, which is 2.5, times our step size, which is 0.5, plus y1, which we calculated to be 4. All right, so at the end of the day, when we simplify all of that, we should get 5.25. All right, so let's come back up. Let's put this on the graph. All right, so maybe like here is 5, so 1 and then like 5.25, maybe that's up here. And if we draw the tangent line, okay, that's not a great tangent line. But ultimately, all right, the connection from point to point should be linear, right? Because you're just drawing tangent lines. You're following tangent lines to the next point, whereas your actual solution, particular solution, might look more curvy, or it should look more curvy. Okay? Again, it's an approximation, but at the end of the day, we can say that y of 1 is approximately, right, not equal to, it's not going to be dead equal to, but approximately 5.25. And that'll do it for that problem. Next. Okay, so now we just have a table of data that we need to sort of tease information from, and it's not that bad. All right, so let's get in here a little bit. Woo. Okay, using the table of data below and Euler's method with 2 steps of equal size. Okay, that's important, 2 steps of equal size. Starting at x equals 1, okay, approximate f of 1.4. All right, assume that f of 1 equals -3. Okay, so, all right, we need to start at x equals 1, and we want to approximate at x equals 1.4. So that tells us that we need to travel, right, a distance of 0.4 and use 2 steps. So that would imply to us that we need to use a step size of 0.2. Okay. And then we also have this initial condition of sorts here that we need to satisfy, and that'll give us a starting point. Okay? And so let's just sort of apply what we extracted from the prompt to this table. So we're going to start, all right, at x equals 1. So this is going to be our x naught, y naught. Okay? So we're going to use this. Then we're going to travel a distance of 0.2 because that is our step size. So that is going to take us to 1.2 here. So this is going to be our x1, y1. Then we need to travel another 0.2 because it just said use 2 steps of equal size. So we're going to go from here to here, and that'll be our landing spot, or officially x2, y2. So we're not going to use all of the entries in this chart, and that's okay. Okay? And of course, we know, and I should clarify here that when I say x naught, y naught, y does not refer to this. This is a slope, right? This is f prime, right? But this is the point that will give us x naught, y naught, right? We were told that x naught, y naught is actually 1, -3 up top. So that was maybe a poor choice of notation on my part, but just to clarify, right? X naught, y naught is not the ordered pair 1, 8, right? The 8 is a slope. All right, so, but you're bright. You'll be able to work with that. Okay, so let's start. So we know that y1 will be given by our slope times our step size plus y0. Okay, so y1, well, we need to get our slope, right? So y prime at our starting point at x naught, y naught will be, right? So at 1, -3, let's see. Well, doesn't matter what the formula is, right? Y prime of 1, that's given in the table. It's 8. F prime of 1 is 8. And that's what's nice about the tables. It kind of just lands in your lap. All right, so y1 equals 8 times our step size, which is 0.2, plus y naught, which is -3. So I should just say -3. And when we work that out, let's see, we are going to get -1.4. You can check me on that. That's the only thing about Euler's method, is that like if this number is wrong, the rest of the approximation just kind of spirals out of control. So just be careful. All right, and then our final y value, so y2, will be equal to m times your step size plus y1. I'm not using very calculus-y notation. Ideally for m, I would be using, f prime of x1, but I'm not really good at writing with this pen. Okay, so let's get y prime at the point where x is 1.2, right? Because that's our next x value. And just because, right, the y value that went with it was -1.4, but we don't really need that. Let's go back to the chart, and we can see that f prime of 1.2 is 12. Yay. So let's build that in. So y2 equals our slope of 12 times our step size of 0.2 plus y1, which we calculated to be -1.4. And when we work all that out, that is going to be, wow, a nice even 1. All right? So at the end of the day, we can say that f of 1.4 is approximately 1. Not bad. Okay, next page. All right, so this next example, definitely a little bit more involved than the previous one, and hopefully you can see why. It's because you have a step size of 0.2 and 5 steps, right? N equals 5. That right here indicates 5 steps. Okay? And notice, we're not trying to approximate any particular value. It doesn't say like, oh, approximate y of 3 or whatever, right? It just says approximate the particular solution. So meaning just get a sense of the shape of the curve, all right, of the particular solution to this differential equation that happens to pass through the point 0, 5, all right? So really the point of example 3 is the sketch, okay? And I'm not going to take you through this. It's a lot of writing, and my writing on this is not very good, but, all right, this will be a nice check for you, okay? So I'm going to give you the values for the 5 points that you should have on your graph, or, well, I guess technically 6 points, okay? And then you can try it on your own and see if you can get there, okay? Bam, magic. There you have it in all of its clumsy glory, all right? There's the set of points that you should have plotted on your graph. Notice that you might want to pay particular attention to your scale. There's a very small difference in values, and you would absolutely need your calculator for this. We would not be asking you to evaluate the sine of 5 off the cuff, all right? but give it a shot. If you can do this one, you're probably in pretty decent shape. All right, so good luck, do well.